I don't want to just start talking. It felt awkward. So I need to ask. Okay, so right now we're talking about randomized singular value decomposition. But if you weren't here for the last few times, we have this matrix X here, and this matrix X is what we call the data matrix. So each one of the columns is one sample of the data. So some of the examples we went over last time was we'll have like xi is like an image of a face, and this equals like some pixel map that's like 2 dimensions. It has like some value for each. Like this pixel will be darker than this one, and this one will be darker than this one. And then you take this and transform it so that it's one single column of all the pixels. And then what we did was we put this into the matrix, and we used the singular value decomposition of this matrix to show that we could compress the images. But this doesn't need to be an image. It could be many different types of data. It can be like one sample of a fluid flow, or it could be, for instance, like a multivariate time series. And then each one of these xi can just be a single column from the single sample from the multivariate time series. And these are just examples of what could go into a matrix like this. And the reason why we're studying singular value decomposition is because value decomposition comes around or comes up in a lot of data science and engineering problems. Um, so what's motivating this is that if you have like an image of data, if it's an image, these columns of X can become very big very fast. And it's oftentimes not feasible to compute singular value decomposition. So what this is about is creating an algorithm to approximate the non-trivial columns of the singular value decomposition by doing some sort of sampling technique. So when we have this like singular value decomposition, we have just want to recall that we have X can be this data matrix can be approximated by taking the first R singular values um, times the outer product of the columns of the singular vectors, or the columns of the U matrix and the columns of the V matrix. So just so I'm not speaking mumbo jumbo, we have for any matrix, we have that we can decompose it into its like singular value decomposition. So it's the product of a unitary matrix, and then the matrix of the singular values on the diagonal, and then another unitary matrix. So this sigma is just call that k, and then there could be 0 here. There could be 0 after a certain point, but often what we want to do is we want to take this matrix and we want to like rewrite it so that we get this matrix as an approximation. Because if we took this and expanded it out, we would get that the matrix X was just the sum of each of the columns times a singular value. So if we went all the way through the sum, we could do each column by column, take the outer product of each of the singular values. I think I called it k here. So and if you think about how this looks, you get one singular value here, and then we get like this column vector here, and we get this it just gets summed up along those elements, like singular value decomposition. Okay, so now what we can do is we want to actually approximate this matrix X and just look at the most dominant correlations that exist in the data. And we do this by actually truncating this sum here. So we can say that X of R, we're going to let this be the first R columns of U, and then the first R singular values, and then the first R columns of V conjugate transpose. And this matrix actually approximates the matrix X, and this also equals here just the first the sum of the first R singular values. So we're looking for this matrix here that approximates the overall data matrix at a lower rank. But now we also have this problem that if our matrix grows too large, it's still even too difficult to find this R in some meaningful way. So what we want to do is we want to use this randomized singular value decomposition. So our goal right now,
Some number less than n, right? Some number
yeah,
less
it's given.
You're just like picking how much you want to compress.
Yeah, just picking out, but it still could be hard to solve for the matrix U. Maybe I said that wonky.
You're not picking. You're finding you. Think?
Well, to find U to get the first R columns of it could still be very computationally complex. And yeah, I said find R, but I meant find the first R columns of these matrices.
Basically, what your meaning is decomposing to 3 matrices is computationally expensive, right? Is that what you mean by finding R? Yeah, right.
No, finding the singular value decomposition.
Okay.
The tensor decomposition part is next.
Okay.
So I think that's what you're referring to. So anyways, the goal is to approximate X of R without doing the whole singular value decomposition. So we're going to do this in a few steps. Okay, so step 1, we're going to just pick R that we want to pick R that we think captures the most amount of our data. So we're going to capture the rank. We're going to pick a rank R. Then what we're going to do is we're going to choose a random projection matrix. So we're going to use P, a random projection. When I say random projection here, I mean it's actually just like P of ij is like some normally distributed random variable. I'm gonna put 1 there because that's kind of confusing and have all the sigmas. Okay, and then what we're going to do is we're going to project X onto Q. Sorry, getting ahead of myself. Okay, so we're going to use this random projection P, and then we're going to use this to find a Q. Find a Q such that X is approximately Q conjugate transpose X. So we want to find this Q matrix. And right now it's kind of a little wishy-washy on how we're going to do that. But if we just stick with it, we're going to see it. So then for the third step, we're going to project Q, or we're going to project X onto Q by some matrix Y. So this is going to take columns of X onto Q, this Q space, and then we want this matrix Y. Okay, so why do we want that? So then we're going to reconstruct the matrix U, which we're trying to get from this. We're trying to recover information about the first R columns of U without calculating the whole U and the whole singular value decomposition. So we're going to reconstruct U. And we're going to just take this to be Q times UY, when UY is going to be coming from the singular value of this, or the QR factorization of this Y. So, okay, so given X, we're going to get this n by n matrix and a desired rank R. So for the first one, what we're going to do is so from this first part, what we have to do is we have to choose P. And like I said, the obvious thing to do here is just choose like either Pij, like some normally distributed random variable, or it could be like a uniform random variable. These are two of the most common types because ultimately, like the choice of the distribution of the random projection matrix is not going to matter because the likelihood that you're going to just choose this random matrix with like a perfect associations that gives us information about the columns of X is like really low. But what we're going to do is once we have this P, we're going to calculate a new matrix Z, and this is going to be the data matrix projected onto the column space. And then what we're going to do is we're actually going to take the QR factorization of this, and this is going to give us the matrix Q that is telling us, and the columns of Q are orthonormal. So suddenly, even though we have this like random part of this matrix P, suddenly we're getting like an orthonormal column space that's going to give us the information about the matrix X. So we look at how this looks. It's like you have this matrix Z, and there's going to be this big matrix X projected on the small with, acting on the smaller matrix P, and then we're going to take the QR factorization of that. So now what we're going to do to solve out to now what we have to do is find this matrix Y. So obviously all we have to do is we have to project, since we already found this Q, we can just plug this in to multiply our matrix times that, and then we get that X is approximately Q times Y. So now all we need to do now is just calculate the singular value decomposition. So compute and this is where that use of Y matrix that I mentioned before kind of comes into play. So we have this singular. The heck was that? So we have this singular value decomposition of this matrix. Well, now we just have all the pieces that we need. So gonna mix these.
Good question. So
Uh-huh.
the QR is the QR decomposition. What's the other one? XP? Um,
Which one are you talking about?
like, can you go a little bit higher up? Yeah. So XP equals QR. I'm not sure that what's XP. Is it?
This is this is the matrix with this is the random projection matrix.
Okay.
So we have here that this is the P matrix. So this is like this has all entries that are like randomly. It's just all the entries of this matrix are random samples
Mhm.
or random variables, and then by multiplying that out and then doing the QR factorization, we get this other matrix Q that has an orthonormal column space, and then we can form this new matrix Y, where by taking this Q conjugate transpose times X, the original data matrix, and then we have that, well, this matrix X is approximately this matrix. And then we have to just compute the singular value decomposition. And well, now we have this matrix Q, and we have this matrix U sub Y. So what we can do is we just say, okay, now U equals QUY. And if we look at how this looks, like in terms of like tall, skinny, fat matrices, which are like weird terminology, but it's what it is. So we have this matrix Q of T, and then we multiply this by our data matrix, and then this equals this matrix Y, and then this equals U sub Y, sigma, and then BT that we found above. And this gives us the singular values up to some R for the matrix by taking this like this random projection matrix.
Let me ask you a question. Does this mean that when you say project, that's starting to just
Yeah, yeah, just multiply it. So anyways, this is an easy way to find the up to R singular values without calculating the whole thing. And then part of this process for doing this random projection is we also take this matrix. We also want to calculate the power iterations. Because we're taking we're finding the first, we're approximating the first R columns of the matrix, the first R columns of the matrix U. But how do we know now that we captured a big enough R? And the way we do this is with this pre-processing step of the matrix X. And what we do is something called power iterations. And we take, it's written like this, like X to the power of Q in these brackets. And that just equals X times X conjugate transpose to the power Q times X. And the bounds on this basically give us that when you do the singular value decomposition of this new matrix, you get U 2Q plus 1. So the singular values in this matrix get raised to the power 2Q plus 1. So this reduces the overall long-term variance of the singular values as Q goes really high. So if you go here, this makes more sense if you look at this code. And this is in the repo here. I have like there's some code for randomized singular values, and I got this cool picture of Spider-Man. And if you click on this button, Open Collab in your browser, it will actually just open this notebook in your web browser, and we can like participate in this like live coding thing. But yeah, this will go through all this example, and what I'm doing is right here I'm just doing the imports. And then I have this URL where this cool picture of Spider-Man lives. And this code here is just to this block of code here is just pulling in the image from the internet, and it's putting it into this image object. So NumPy, if we start at the top, NumPy is just a standard scientific computing library. Check. Matplotlib is just a plotting library in Python. And this image read is a part of that library to read in images. Now this library here, PIL, this is an image processing library in Python. And then if you get this image here, or this import here, requests, that's just to pull in data from the internet. And this this from IO import bytes IO, that's just to deal with the image as bytes instead of just pixel match or something. So here what I'm doing is I'm converting the image to a NumPy array. And then we're calculating the mean of the image. And then this is what it looks like once we remove the mean and we removed all the color. Well, suddenly I got the same cool picture of Spider-Man, but it's black and white. Now what we're going to do is we're going to make this function here that's a randomized SVD function. So if you remember the whole rigmarole we did earlier, well, this takes in X, which is the data matrix. And right now it's just a single image. And it's going to take in R, which is 400, it's the target rank. And the number of power iterations is going to be 1, and the oversampling parameter is going to be P. I didn't go in, nor did I write down what the oversampling parameter does. But this is going to go in, it's going to calculate the random singular value. So if you go into how this function works, right here I'm calculating, so I have P equals np.random. That's the part that I'm just calculating the normal. It's going to be a matrix of ny by r plus p. That's going to give us, so this oversampling parameter is going to be like slightly higher than the value r that we think will capture all the data. And this is making a matrix that's going to look like this. There's just a bunch of random variables here. Call it x. Don't necessarily care about what's in here because it's going to go through and then we're going to calculate this matrix Z. As promised, we're just going to take the matrix product of both these. And then for each of the power iterations, we're going to go through and we're going to like raise this value Z to the number of, to this, to x times x transpose. And then what we're going to do is we're going to calculate the singular value decomposition on that, on this y, get uy, and then we're going to approximate u is going to be u times this matrix uy, similar as we showed in the math. Then we're going to return u and this matrix S, which is S for sigma, and then VT, which is V conjugate transpose. So those are the singular vectors in type 2 matrices and the approximated singular values. And then what we're going to go through is we're going to reconstruct the image, and we're going to compare it to just doing a regular singular value decomposition, because this is like a toy problem. We don't actually need to worry about the computational cost here. So we're just going to do a regular. Oh, I'm sorry, I'm not doing that at all. I'm just, yeah, this is calculating the error bounds. I didn't go over what the error bounds are because I wanted to get to tensors more. So anyways, this is showing the reconstruction of based on truncating the R values for each one of these. So this is X, and then this X SVD, and then XR SVD. XR SVD is just the random singular values taken multiplied by this image to reconstruct the approximation of the image. And that's the randomized singular values in a nutshell. And I'm just going to kind of run through the rest of this because I want to get to the tensor part. So here I'm calculating the full SVD. And then what I'm doing is I'm calculating values of Q, the power iterations, that show how much the power iterations converge more quickly to the actual singular values of the matrix by taking higher and higher powers of Q. And that is, in a nutshell, the power iteration algorithm in randomized singular values.